Hi, everyone, and thanks for attending this talk. I am Anrin, a postdoc at Duke University, and today I'll be talking about Perl, a plausibly deniable flash translation layer. This is work which was done when my colleague Chen and I were doing our PhDs at Stony Brook University with our advisor Radu, Sion. So the high-level motivation behind this work is to build a secure system which provides privacy against coercive adversaries who can coerce the users to hand over encryption keys for her data. This comes at a time when we are observing more intrusive privacy laws which require users to hand over their keys on demand, and increased instances of unlawful detention and searches in oppressive regimes. Clearly, in all these cases, we need something more than conventional encryption, because once the user hands over her keys, then there is no guarantees for her plain text data. This is where plausible deniability comes in, and plausible deniability has been defined as a security property that allows a party to claim to others, potentially adversaries, that some information is not in their possession or that some transaction has not taken place. In this work, we are mainly concerned with storage level plausible deniability, where a user wants to store some data on a storage device using a plausibly deniable storage system, or PDS system in short, and the user later wants to deny the presence of some certain piece of information on her storage device. The adversary can observe the storage device multiple points in time and compare snapshots to see what has changed, but the adversary cannot observe the device at runtime, which means that the adversary cannot observe the state of the memory and the caches while the operations are being performed. By the same token, the adversary cannot compromise the system by installing malware, spyware, etc. The adversary can, however, coerce the user to provide her keys and passwords on demand, but the adversary is rational, which means that when the user provides her keys and is able to convince the adversary that there is no other data on the device, then she will not be subject to any more rubber hose attacks. Now, this is how a typical plausible deniability system works in the wild. So it allows the user to store data encrypted either under a public key or a hidden key. When the user is asked to hand over the device, then she hands over the device along with the public key and claims that there is no other data on the device. Now, a PDS system is supposed to guarantee that the adversary cannot guess whether there is any more data on the device with non-negligible advantage, and therefore guess whether there is, or determine whether there is a hidden key that the user is hiding. Now, there is a long line of work on building plausibly deniable storage systems, which can be broadly classified into steganographic file systems and hidden volumes. A prominent example of a hidden volume-based solution is TrueCrypt, where users are allowed to create multiple logical volumes encrypted under different passwords. Some of these volumes can be marked as hidden. When an adversary coerces the user for a password, she provides the passwords for her public volumes and claims that there is no other data on the device. Now, most of these solutions actually do not work for flash-based devices. In fact, the only secure plausibly deniable storage system for a flash-based device is the solution due to GI et al. From CCS 2017 called DEFTL. But as I will show you in a few slides, even DEFTL does not protect against all types of adversaries. So what makes flash devices different? In case you do not know how a NAND flash device works, here is a quick 30-second crash course. So flash devices are made up of cells, which are the basic unit of storage. A cell is simply a floating gate transistor, and depending on the amount of charge that you store on the floating gate, the cell is interpreted to be either in a state of 0 or a state of 1. A group of cells make up a page, and a group of pages make up a block. Now, in a flash device, the writes are performed at page level granularity through an operation called programming. However, during a programming operation, you can only take the cells which are in a state of 0 to a state of 1, but you cannot take any cell which is in a state of 1 to a state of 0. For this, you first need to erase the cell, and erases can only be performed at the block level, which makes them slow, and repeated program and erase cycles for a block reduces the lifetime of the block. So keeping all these peculiarities in mind, a flash device requires a flash translation layer, or an FTL, to work. An FTL is simply an interface between the file system and the raw flash device. It maps data to the flash device while making sure that the wear is uniformly distributed. Due to this, the data that is updated in the flash device may not be updated in place. To ensure that no old invalid data remains on the flash device, the FTL also performs an operation called the garbage collection. Now, all this is fine, except for the fact that the presence of this FTL and the address translation that it performs conflicts with upper layer deniability logic. This is because now the file system does not have any control on where data is actually ending up on the flash device and where and when old data is actually getting overwritten. So Perl starts with a simple idea, which is if you want to implement deniability for flash devices, the best place to implement this logic is in the FTL. And we are not the first to come up with this idea. DEFTL from CCS 2017 is also an FTL with plausible deniability. However, it only provides single snapshot deniability, which means that if the adversary is able to observe the device more than once, then DEFTL cannot hide the changes to the hidden data. Perl, on the other hand, is multi-snapshot resistant, which means that all changes that are performed to the device can be attributed to only public data operations. Now, the key idea in Perl is to use a data encoding scheme where code words encoding both public and hidden data can be attributed to a code word which is only encoding public data. For this, we use WOM codes. So write once memory, or a WOM code, is a special encoding scheme specifically designed for write once memory devices like a flash device, where you can encode, where you can turn a 0 to a 1, but you cannot turn a 1 to a 0 without performing an erase. A WOM code simply allows more writes before you have to perform an erase. So I'll give you an example of a 2-3 WOM code. Now, a 2-3 WOM code represents each 2 bits of logical data with a 3-bit code word. And the code word that is used to represent the logical data depends on the state of the page to which the data is being written. For instance, let's start with an empty page. Now we want to write the logical data 0, 1. In this case, using the first write representation of 0, 1, the page transitions to a state where now the code word stored is 0, 0, 1. Now let's say we want to write 1, 0. In this case, using the second write representation of 1, 0, the page transitions to a state now storing 1, 0, 1. After this, we cannot perform any more writes, so this page needs to be erased. But note that performing writing 0, 1 and then subsequently 1, 0 in a flash device without a WOM code would require an erase in between. Now, the key idea in Perl is we observe that WOM codes can also provides an additional capacity for storing hidden data. Specifically, what we can do is we can make sure that a page which has been written twice with public data looks indistinguishable from a page which has been written once, storing both public and hidden data. In this case, the second write representation of the WOM code depends on the hidden data that we are trying to store. So, for instance, this is the same page transition that we observed in the last slide. In this case, the final state of the page stores the code word 101. But given the truth table that you see on the left, the same page, we can reach the same state of the page if we were storing the logical data 10 along with one hidden bit 1. Now, given the final states of these pages, an adversary cannot distinguish whether this page has been written twice with public data or once with public and hidden data. Of course, this sounds simpler than it really is, because we find out that not all WOM codes work. In fact, the WOM code that we have been discussing so far does not solve our purpose. What we actually require is to ensure that the distribution of code words encoding only public data is the same as the distribution of code words encoding both public and hidden data. A WOM code that allows that has this property is called a WOM code with equal partitions. So I'm not going to go into the detail, but we theoretically show in the paper that any WOM code that satisfies this property can be used to build a plausibly deniable storage system. So based on this idea, we come up with a 3-5 WOM code with equal partitions, but I'm not going to go through I'm not going to go into details of how this WOM code is built. And since Perl is actually an FTL, so it needs to perform, it needs to solve many other challenges, which includes page allocation and transition, garbage collection, and where leveling. Now we need to ensure that all these processes are independent of the presence of hidden data on the device. I'll encourage you to take a look at the paper for more details on how this is done. Now we have implemented Perl and benchmarked it for both micro benchmarks and application benchmarks. What I'm going to talk about today is the overall throughput. This is a micro benchmark, and what we measure is the IOPS for both reads and writes. Our baseline is DFTL, which is an open source Linux-based FTL implementation. And what we find is that for public data operations, Perl is less than 2x slower than DFTL. On the other hand, for the hidden data operations, Perl is 5x slower than DFTL for the reads and around 12x slower for the writes. The higher overhead for the writes is due to the fact that while performing a write, Perl also needs to perform several other bookkeeping operations like page allocation. So in conclusion, Perl is an FTL with multi-snapshot plausible deniability. We are able to build a system which is resilient to multi-snapshot adversaries with a novel use of WOM codes. And we show through experiments that Perl is practical for public data use and has reasonable overheads for hidden data use. So that's all I have. Thank you, and I'll be very happy to take your questions.